In this talk, I want to demystify the burning sensation you feel during those final reps of a tough set. Many athletes and coaches still blame lactic acid for the searing burn and think that novices feel it more than advanced lifters. But is lactic acid really to blame? Today we'll decode the science of fatigue, acidity, and muscular burn. By understanding what's happening inside your muscle cells when you push to exhaustion, you'll learn how to manage the burn, train smarter, and use supplements strategically. Let's begin by addressing one of the most persistent myths about exercise, that lactic acid causes the pain and forces you to stop. One of the most enduring beliefs in fitness culture is that lactic acid buildup causes the burning sensation in your muscles and makes you stop a set. You hear people talk about flushing out painful lactate after training, or assume that only beginners feel the burn because their bodies can't handle it. These ideas are outdated. Lactate isn't the culprit, and advanced lifters still feel discomfort when they train near their limits. We need to reframe our understanding of what's really happening when your muscles ache. To do that, we'll start by revisiting the energy systems that fuel intense exercise and see where lactate fits into the picture. When you explode into a heavy set, your muscles demand ATP, the molecule that powers contractions at a rate far beyond what you need at rest. For the first few seconds, you draw on phosphocreatine stores to rapidly regenerate ATP. However, these stores empty within moments. As they diminish, your muscles shift to glycolysis, breaking down stored glucose to meet the demand for energy. This switch allows you to continue producing ATP quickly, but it also sets the stage for changes in acidity and metabolites that contribute to fatigue. Understanding this transition from the ATP-PCR system to glycolysis is essential for appreciating why muscles begin to burn as a set progresses. We'll delve deeper into glycolysis next. Glycolysis is a pathway that rapidly breaks down glucose to produce energy in the absence of sufficient oxygen. Through 10 enzymatic steps in the cytosol, one glucose molecule yields 2 molecules of pyruvate, 2 ATP, and 2 NADH. When oxygen delivery can't keep up with demand, pyruvate is converted into lactate. This reaction regenerates NAD+, a cofactor necessary to keep glycolysis running at high speed. Importantly, this conversion produces hydrogen ions but also consumes them, helping to maintain the cellular redox balance. Understanding glycolysis' role in energy production explains why your muscles can keep contracting after phosphocreatine is depleted. Next, we'll look more closely at lactate formation and how it supports ongoing energy production. During intense exercise, the enzyme lactate dehydrogenase converts pyruvate into lactate while oxidizing NADH back to NAD+. This regeneration of NAD+ is crucial because it allows glycolysis to continue producing ATP quickly in low oxygen conditions. Contrary to popular belief, lactate formation actually consumes protons rather than releasing them, helping to buffer cellular pH. Once formed, lactate doesn't stay locked in the muscle. It enters the bloodstream and can be transported to other tissues like the heart, brain, and liver, where it is oxidized for energy or converted back into glucose via gluconeogenesis. Recognizing that lactate is part of a recycling system, not a waste product, sets the stage for debunking the term lactic acid, which we'll address next. The terms lactic acid and lactate are often used interchangeably, but they are not the same. Lactic acid is a molecule that dissociates into lactate and a hydrogen ion at physiological pH. In reality, virtually no lactic acid exists in your muscles or blood under normal conditions because it dissociates immediately. Lactate itself acts as a strong base, helping to buffer acidity rather than causing it. Blaming lactic acid for muscle burn is therefore scientifically inaccurate. By understanding this distinction, we can better appreciate lactate's supportive role in metabolism. The real culprit behind the burning sensation is the accumulation of free hydrogen ions and inorganic phosphate, as we'll discuss in the next slide. The burning sensation you feel near the end of a set is primarily caused by a buildup of hydrogen ions inside your muscle cells. As glycolysis accelerates and ATP is hydrolyzed, protons accumulate and intramuscular pH drops. These hydrogen ions bind to contractile proteins and enzyme sites, interfering with their function. At the same time, inorganic phosphate from phosphocreatine breakdown accumulates and further reduces force production. Together, proton accumulation and increased pi make each contraction feel more difficult and diminish your ability to generate force. So while lactate is produced during intense exercise, it isn't causing the burn, it's the acidity and phosphate that limit performance. Next, we'll explore how this acidity impairs muscle function at the molecular level. When muscle pH falls below about 6.5, the ability of contractile proteins to interact with calcium declines. hydrogen ions and dihydrogen phosphate reduce the sensitivity of the contractile apparatus to calcium, meaning more calcium is required to achieve the same force. This reduction can lower maximum force output by roughly 12 to 22%. Fast twitch fibers are particularly sensitive to acidosis, which is why explosive performance drops off rapidly when you're fatigued. Additionally, elevated acidity slows the rate at which cross bridges form and detach, impairing both contraction and relaxation. These molecular effects explain why the burn feels so intense and why performance deteriorates as pH drops. Now that we've established lactate isn't the enemy, we can explore its positive roles. Rather than being a metabolic villain, lactate serves several important functions. Oxidative fibers, the heart, the brain, and kidneys can use lactate as a direct fuel source, converting it back into pyruvate and oxidizing it to generate ATP. In the liver, lactate acts as a gluconeogenic precursor, being converted into glucose through the Cori cycle to maintain blood sugar levels. Lactate also functions as a signaling molecule, modulating gene expression and metabolic pathways to facilitate adaptation to training. Recognizing lactate's roles as fuel and messenger underscores why it's a friend rather than a foe. Next, we'll look at how lactate is transported and used throughout the body in what's known as the lactate shuttle. Lactate produced in fast twitch fibers doesn't stay put. It exits these fibers via transporters like MCT4 and enters the bloodstream. From there, it travels to other tissues where it is taken up via transporters such as MCT1. Slow twitch muscle fibers, which have high oxidative capacity, use lactate as fuel by converting it back into pyruvate and feeding it into the Krebs cycle. In the liver, lactate can be converted into glucose and released back into circulation to support ongoing exercise. This coordinated movement of lactate, often called the lactate shuttle, illustrates how different tissues share metabolic intermediates to maintain performance. Understanding these pathways shifts the narrative from seeing lactate as a waste product to viewing it as an energy currency. Now let's consider other factors that limit your repetitions. Several factors converge to limit how many reps you can perform. As phosphocreatine stores deplete, inorganic phosphate accumulates inside muscle cells and reduces force production. As muscle glycogen levels drop, the ability of glycolysis to maintain high rates of ATP production declines, and calcium release from the sarcoplasmic reticulum becomes less efficient. Central fatigue plays a role as well. Motor neurons may fire less frequently, reducing drive to the muscles. Together, these local and neural factors decrease your capacity to maintain intense contractions. Understanding these mechanisms provides insight into why training strategies and nutrition, such as maintaining glycogen stores, can influence endurance. Next, we'll look at how your body naturally buffers acidity and what you can do to enhance these systems. To cope with the surge of hydrogen ions during intense exercise, your muscles rely on intrinsic buffering systems. Molecules like bicarbonate, phosphate, and carnosine act as proton acceptors, preventing pH from dropping too quickly. These buffers help you continue contracting for longer despite rising acidity. While your body can synthesize and adapt these systems to some degree, nutrition and supplementation can also influence their effectiveness. In the next few slides, we'll explore one of the key intramuscular buffers, carnosine, and how you can enhance its capacity through beta-alanine supplementation. Carnosine is a dipeptide made from beta-alanine and histidine, and it is concentrated especially in fast twitch muscle fibers. Its pK of 6.83 makes it an effective buffer at the pH range, where fatigue begins. During high-intensity exercise, the imidazole ring on histidine accepts hydrogen ions, delaying the drop in pH. Beyond buffering, carnosine regulates calcium release from the sarcoplasmic reticulum, modulates enzyme activity, and functions as an antioxidant. Because carnosine levels are higher in muscles used for explosive efforts, enhancing its concentration can help you sustain performance. To increase carnosine stores, you need to increase availability of its rate-limiting precursor, beta-alanine, which leads us to the next slide. Beta-alanine is a non-essential beta-amino acid and is the rate-limiting substrate for carnosine synthesis. When you ingest beta-alanine, it combines with histidine inside muscle cells to form carnosine. By supplementing with 2 to 6 grams per day over 4 or more weeks, you can increase intramuscular carnosine concentrations by 20 to 80%. This translates into improved high-intensity exercise capacity and prolonged time to exhaustion during sprints or repeated bouts. Beta-alanine is safe for most people, although it can cause a harmless tingling sensation called paresthesia. Increasing carnosine through beta-alanine is an effective strategy for improving buffering capacity. Next, we'll look at the evidence supporting beta-alanine's performance benefits. Controlled trials confirm that beta-alanine supplementation enhances performance in high-intensity tasks. Studies report that athletes who supplement with beta-alanine improve their time to exhaustion and raise their ventilatory threshold compared to those taking a placebo. In practical terms, participants perform more repetitions or repeat sprints with less decline in power output when their carnosine stores are elevated. These benefits underscore the role of intracellular buffering in delaying fatigue. However, beta-alanine doesn't replace the need for proper training and progressive overload. It simply provides a biochemical edge. Next, we'll discuss how training itself adapts the body to raise the lactate threshold and delay the burn. Your body naturally adapts to regular endurance and resistance training by increasing the number of mitochondria and blood vessels in your muscle fibers. These adaptations improve oxidative capacity and enhance the muscle's ability to use oxygen efficiently, which delays lactate accumulation and improves clearance. Hormones and metabolites such as epinephrine, calcium, and ADP/MP stimulate glycolysis, but training shifts the lactate threshold to a higher intensity. As a result, you can work harder before acidosis and fatigue set in. This is why consistent training combined with proper recovery raises your tolerance for the burn. Next, we'll look at specific strategies and supplements you can use to delay the burning sensation even further. Several strategies can help you delay the onset of muscular burn. First, supplementing with beta-alanine raises carnosine stores, improving your muscle's ability to buffer hydrogen ions. Second, using extracellular buffers like sodium bicarbonate or sodium citrate before high-intensity efforts can help neutralize protons in the bloodstream, although they may cause digestive discomfort in some people. Third, pacing strategies. Alternating bouts of high and low intensity allow your body to clear metabolites during easier intervals. Finally, giving yourself adequate rest between sets restores phosphocreatine and helps clear accumulated hydrogen ions. Combined with training adaptations, these tactics enable you to push harder for longer. Of course, how you perceive the burn also matters, which leads us to the mind-muscle experience. The sensation of burning is not just a biochemical event, it's also a psychological experience. Feeling the burn signals high effort and metabolite accumulation, but it doesn't necessarily mean you're building more muscle. Mental toughness and an internal focus can help you push through discomfort and finish a set. Being aware of the sensations and learning to embrace them may improve your ability to train near your capacity. However, equating burn intensity with muscle growth is misguided. Growth still depends on mechanical tension and overall workload. Keeping this perspective ensures that you use the burn as a guide rather than a goal. Next, we'll revisit the question of whether the burn itself drives hypertrophy. Metabolic stress, the accumulation of metabolites, cell swelling, and hormonal changes can contribute to muscle growth by activating signaling pathways like mTOR and MAPK. However, this metabolic stress isn't essential if your training provides sufficient mechanical tension and volume. Mechanical tension remains the primary driver of hypertrophy. Without progressively heavier loads or increased volume, metabolic stress alone won't build muscle. That said, incorporating high rep sets or short rest intervals for metabolic stress can add variety and may augment growth. The key is to see metabolic stress as an adjunct to, not a replacement for, tension and volume. With that clarity, we can move on to practical training recommendations. How do you apply this information in the gym? First, prioritize progressive overload. Gradually increase the weight you lift and track performance gains. Second, periodize your training by mixing heavy strength work with high rep pump sessions to target different stimuli. Third, use buffering supplements like beta-alanine or sodium bicarbonate judiciously, being mindful of potential side effects. Finally, develop mental strategies to embrace discomfort without equating burn with success. Focus on technique, breathing, and pacing, and use the burn as feedback rather than the sole indicator of a good workout. These practical steps will help you train more effectively. We're almost done. Let's summarize the key points. To wrap up, remember that the burning sensation during intense exercise is caused by hydrogen ions and inorganic phosphate, not by lactate. Lactate itself is a valuable fuel and signaling molecule. Your muscles have natural buffers like carnosine that help manage acidity, and these can be enhanced with beta-alanine supplementation. Consistent training raises your lactate threshold and improves clearance, allowing you to work harder before fatigue sets in. Most importantly, hypertrophy and strength are driven by mechanical tension and volume, not by how much it burns. Use the burn as a signal to guide your effort, but don't let it distract you from the fundamentals of progressive training and recovery. Our final slide ties this message together and invites you to reflect on your own experience with muscle burn. Ultimately, the burn isn't your enemy, it's a signal that your muscles are working hard and that hydrogen ions are accumulating. Instead of blaming lactic acid, learn to harness that signal and train your body and mind to tolerate it. With proper understanding and smart training, you can raise your threshold and turn discomfort into progress. If you appreciated this evidence-based insight, please subscribe for more. Share your stories of muscle burn in the comments, and send this presentation to a friend who still blames lactic acid. Together we can spread accurate information and help each other train smarter. Thank you for listening and keep pushing towards your goals.